Welcome to this lecture about local discomfort. We have discussed in a series of lectures how to estimate and assess comfort using the Fangers model. However, there are some simplifications in this model, by which it cannot catch all detailed properties of the indoor environment influencing the comfort. In this lecture, you will learn how to correct for these simplifications and how to address what we call local discomfort. One of these simplifications concerns air temperature. The air temperature in Fangers' model is considered to be uniform in the room volume. However, there may be large vertical temperature gradients. As you know, warm air rises, and that does mean something for the feeling of comfort. Another simplification is about air velocity. Fangers' model does not consider the turbulence of the air, while people are quite sensitive to it. Finally, you may remember that in Fangers' model the mean radiant temperature MRT is used. But people also are sensitive to asymmetry in the surface temperature. Even when Fangers' models predict comfort, that is when temperature, MRT and humidity are in the comfort range in the diagrams on the right, it may be that people experience discomfort. Therefore, when the parameters are in the comfort range, engineers and indoor environment experts would always make an additional analysis of the following four characteristics. First, large vertical air temperature gradients. Second, turbulence in the air. Third, large radiation asymmetry. And four, a too low or too high floor temperature. We are going to address each of them starting with vertical gradients. In Fangers' model, the assumption was that the air in the room is just one temperature. The temperature is the same everywhere. But as you may know, warm air rises, and in a room one can expect the air to be warmer at the ceiling level than on the floor. That is why heating systems like radiators or warm air from convectors are generally placed close to the floor to ensure a better mixing of the air. Generally, it is very unpleasant to have a warm head while the feet are cold. Experiments were carried out with people in a state of thermal neutrality, which were exposed to vertical temperature gradients, and there is a relationship between the percentage of people dissatisfied and the temperature difference between head and feet. You see on the x-axis the temperature difference between head and feet. In this graphic, the head temperature is always higher than the one of the feet. The opposite would not create discomfort. For instance, if the temperature at head level is higher by almost 3 degrees Celsius than the temperature at ground level, this will lead to 5% of people dissatisfied. If the temperature difference is 5 degrees, the percentage of dissatisfied increases enormously and is around 24%. So, in case of comfort complaints, this is certainly a parameter to measure. We saw in another lecture that people are sensitive for too high air speed. Sensitive spots are the neck and the ankles, and we named this discomfort draft. A general rule is that the airspeed should be lower than 0.15 meters per second in winter, and a higher velocity is allowed in summer. But draft depends also on the turbulence of the air. Turbulence is a measure for changing speed and direction of air flows. If the flow is laminar, which is often the case with natural ventilation, the flow is very steady in its direction and velocity. If the flow is turbulent, at the same average velocity, many changes in air direction and local velocity will take place, increasing the sensation of draft. This is the type of flow observed when a fan or a ventilator is used. The turbulence intensity, TU, is defined as the ratio of the standard deviation of the air velocity to the mean air velocity. The figure gives the relation between air temperature on x-axis, the average airspeed on the y-axis, and the turbulence intensity, which are the lines in the graphic. This graphic was drawn for 15% of people dissatisfied. It should be interpreted on the following way. For example, if the airspeed is 0.2 meter per second and the turbulence intensity is 10%, an air temperature of 21.5 degrees Celsius will ensure that no more than 15% people are dissatisfied. If the air temperature drops below this value, more people will be dissatisfied, and if the air temperature increases, less people will be dissatisfied. If the turbulence increases, for instance, to 20%, then a much higher air temperature of 23 degrees is needed to maintain comfort in such a way that only 15% of people are dissatisfied. Complaints about radiant asymmetry arise when there are too large differences between surface temperatures, even if the MRT is in the comfort range. The MRT is the average radiation temperature. As you know, the average between 22 and 18 is 20 degrees, but 20 degrees is also the average between 10 and 30, which will not produce the same effect on comfort. This radiant asymmetry may happen, for instance, when the ceiling has a too high temperature. In a hot climate, this can happen if the ceiling is not insulated and absorbs a lot of solar radiation. In cold countries, it can also happen in case of cold windows. In the figure, the relationship between the percentage of people dissatisfied and radiant asymmetry is shown. Radiant asymmetry is defined as the difference in surface temperatures between the surface under consideration and the surface in the opposite direction. When the wall or ceiling is said warm, the asymmetry on the x-axis refers to a positive temperature difference. When the wall or ceiling is said cold, the asymmetry on the x-axis refers to a negative temperature difference. Let's look at a few examples and start with the warm ceiling. The radiant asymmetry in that case is the temperature difference between ceiling and floor. If we want no more than 10% of people to be dissatisfied, the temperature of the ceiling should not be higher than the floor temperature plus 6 degrees. For a cold ceiling, the temperature of the cold ceiling should not be lower than the floor temperature minus 15 degrees. By comparing these two examples, one can deduce that people are bothered more by warm ceilings than by cold ones. For a cold wall, the radiant asymmetry is the temperature difference between the wall and the opposite wall. For 10% dissatisfied, the temperature of the cold wall should not be lower than the temperature of the opposite wall minus 12 degrees. Finally, for 10% dissatisfied, the temperature of a warm wall must be maximum 31 degrees higher than the temperature of the opposite wall. So we can conclude that people like warmer walls much more than colder ones. In ISO 7730 standard, the recommended maximum surface temperature asymmetries are for cold walls 10 degrees and for warm ceiling 5 degrees, corresponding to 8% of people dissatisfied. We are now coming to the last cause of local discomfort, the floor temperature. Due to the direct contact between feet and floor, local discomfort of the feet can be caused by a too high or a too low floor temperature, especially in bathrooms or with floor heating. It is caused by conductive heat transfer from the feet to the floor, which is not accounted for in Funger's model. The heat transfer depends also on the conductivity and the heat capacity of the material the floor is made from. From everyday life, we know that cork floors are so-called warm and marble floor feels cold. The figure gives the relation between the percentage of people dissatisfied and the floor temperature. Observe that even at the optimum floor temperature of 24 degrees Celsius, 6% of people are still dissatisfied. The figure explains why floor insulation is very important. It also explains why floor heating should be low temperature heating at no more than 30 degrees. To summarize, this lecture was about local discomfort, which may arise while the thermal comfort is right according to Funger's model. This local discomfort can be caused by vertical temperature gradients, turbulence of the air, radiant asymmetry, and a too high or too low floor temperature. For each of these 4 causes of local discomfort, we studied diagrams that can be helpful to assess comfort complaints. Thank you for your attention.